Okay, so we will continue with this. You still stick, you will stay with 0.1?
Minus 0.2.
Minus
0.02.
5.2, huh? Yeah.
No, this is what is optimum?
Good, minus 0.98. What is the correct answer for x2? Okay, 0.49. But is it going in the right direction? The answer is, it's fine, no? Okay. Good, minus 0.68. 0.05. Hey, what does it tell you? dy by dx2 is 0.05. We are very close. But we can't go home because this fellow has not become close to 0. We will stay with 0.1. 1.7 10 to the power of minus 4, what is it? 7.4 into 10 to the minus 3. 0.49. It's all minus, no, still? 4.8,
4.8.
See, now it is becoming sluggish, right? 1 to 0.6 was rapid, this is also rapid, now it becomes sluggish. The answer is 0.45. It becomes slow, that is the way it works. Okay, when it gets close, then it goes like this. Okay, so I think some people, you must have got some ideas. Why don't you directly go like this? If you know the two, this thing, why can't you skip this and go straight? It is. Yeah, we can do that. That is called the conjugate gradient method. I am coming to it. That is called the Davidson-Fletcher-Powell method. How people have thought about it and, okay. So that is an advanced version of this. Okay, 1.5, 0.48, and now. Oh, it is bad. Now 0.21 it goes like mad, no? What happens if it's 0.1? Now I will make it 0.05 now.
Minus 0.06.
Minus 0.06 means 0.42 it becomes. No, I will now do some cheating, so I will make this 0.05. Yeah, I can change delta x1, right? Because I know that it is converging. Now tell me. 0.0? .03. How many of you are working out? Minus 0.03. Okay. So 1.6, 0.45. Not yet, huh? dy by dx1 must be close to 0 now, no? How much is it? Minus 0.3. This fellow? Minus 0.37. Wait here. Now for the first time dy by dx For the first time dy by dx2 is changing sign, right? Please look at the board. For the first time dy by dx2 is changing sign. It is telling us that we have overshot the answer. What is the actual answer? 0.455 something. Huh? Yeah, because very close to it won't be. So you still want to stick to the 0.05? 0.05 you want to stick, okay. Now it will become, so there will be a positive correction to it, correct? Huh? Then it becomes 0.51, huh? No, I don't like it, so I will make it 0.02. See, that is why in order to adjust this, your delta x1 will reduce, so it will take more and more iterations. See, you came very quickly to 1.5, now 1.55, 57, 58, 58, to reach 1.62 will take a long time, 1.64 will take a long time for you. What is this? We will stop with one more iteration. Point? It is a positive correction, right? Yeah, now this will become 1.57, 0.475. Now we will stop with this iteration because all of you got a good idea of how it works. Yeah, now complete this dy by dx1. No, if it becomes minus, that means you have to change the delta x1 because x1 x2 have to be that is all okay. X1 x2 should not become
minus 0.14, 0.35.
Now it is rapidly oscillates, no, it oscillates too much, so again I will make it 0.01. Yeah, not 25. It again becomes negative, okay. Now it comes back to 0.45, it will keep on oscillating, this will slowly go to 1.64, it will take another 8 iterations, but this is the way it goes. Now it is going in the right direction, but it is going slowly towards the end. It will start off very fast, it is very impressive in the beginning and then it becomes very slow, okay. So this is the Cauchy's method. I hope all of you got an idea of this, okay. Now how to incorporate alpha and solve this problem? How to incorporate alpha and solve this problem? Okay, now okay. At 1 1, what is the value of dou y by dou x1? Minus 1. Now choose alpha such that delta x1 is dy by dx1 into alpha, delta x2 is dy by dx2 into alpha. So x new will be x old plus delta x1, that is alpha times dy by dx, okay, alpha times dy by dx1 minus 1, alpha times dy by dx2. Now I will say y equal to solve it for alpha. Once you get the value of alpha, you will get the values of new values of, but see how difficult it is. Now solve, getting alpha itself is a project now, you have to use golden section search, but if you have patience, if you do it within 2 iterations or 3 iterations, you will get what you, but what took you 15 iterations, okay. So dy by d alpha, dy by d alpha equal to 0, okay, solve for alpha. Okay, it is not appealing because you do not know after getting this alpha whether we are better off compared to the, so we will try it on some problem where we know the final answer and we can at least one iteration we can calculate the value of alpha, even though the problem may be silly, alright. Okay, now you got the point. Now you will get, so you once you calculate alpha, the new value of x1 will be 1 minus alpha, the new value of x2 will be 1 plus 4 alpha, you proceed, okay, get dy by dx1 dy by dx2 at the new values of x1 x2, get the new values, so every dynamically the alpha will be updated, you solve for alpha, that is it basically, you convert it into a single variable optimization in alpha each and every iteration and use the most sophisticated single variable search to get the value of alpha. This is the clinically correct Cauchy's method. What I taught you before is not the actual method, but it becomes very difficult, that is why I taught that first, okay. Let us try this. So this is the Cauchy's method, okay, what I have told you is the Cauchy's method. If you look at any good optimization book, they should have explained Cauchy's method like this. Okay, let us try this. We did this before, okay, x1 x2 greater than 0, this is a circle, right, this is a circle, okay. What is the solution? 8 6, y star y plus at the optimum, very good. So this solution we know. Now we will see how this fellow helps us, how the Cauchy's method will help us. You can start anywhere, let us start with 2 2. Let us start with 2 2, we can get dy by dx1, what is it? What are these fellows now? At the initial guess value, minus 12, minus 12,
minus 8.
okay, very good. Now we have to calculate y at the new points, okay, 2 minus alpha, 2 plus alpha, correct. We have to calculate the y and optimize, fine. So what is this y of correct. Abhishek, is it okay? Now you have to optimize for y equal to no. Now take dy by d alpha equal to 0 and get the value of alpha. What is it now? Minus 10 minus 12, is it? Is it correct? Is that correct? No. So it is correct. So 6 everything can be taken out, right? Don't worry about all this, then dy by d alpha equal to 0, alpha equal to minus half. If alpha is equal to minus half, what are the new values of x? Straight, one hit, target mission accomplished. Straight you get 8 6 answer. You start anywhere, it will come, because function is just a simple quadratic. So I wanted you to believe that this works, that is why I chose this silly example, and it works, right? Okay, so therefore what is it correct? You got the answer, but the previous problem getting alpha was very difficult. This is how it works, but what is the logic behind all this? Why should this, what is this orthogonal property, and what is the vector calculus, what is the mathematics behind this? We will see that, then I will explain the conjugate gradient method and we will close. We are not solving any problems in conjugate gradient, okay. People who want to do your masters or PhD in operations research or optimization, you will do 6 or 8 courses, then somebody will teach you conjugate gradient method. People have worked in between 70s, 80s and 90s, so many papers have been written, so many PhD theses have been produced, how to improve the Cauchy's method. Then came a Newton's method. The Newton's method, what is the difference between Cauchy's method and Newton? Why only the first derivative should be taken? I will take second derivative also, that is a Newton's method. Okay, we will take the second derivative and make it quadratically convergent. Okay, people worked on. Then somebody said modified Newton method, quasi Newton method. Then somebody said I will achieve the performance of the Newton method, but without taking recourse to the second derivatives. I am coming up with conjugate gradient method. So people say conjugate gradient method gives a performance which is very similar to Newton's method, but second derivatives are not required. Like that, people have developed this, and now it is nearly perfect. Many of these, lot of lot of optimization is there in chemical engineering. Are you aware of this? Chemical engineers solve a lot of these problems, big lot of these NLP problems. What are these NLP problems? Non-linear programming. Okay, so now, so you are convinced that this alpha business works, right? Now we should yeah, any doubts? Now there is some we require a proof of this, right? Wait, why does this conjugate, why does the steepest descent method work, or where does it come from? So let us say mathematical consideration. So we have first, I gave the algorithm, we solved a problem, we saw two variants or two variations, and we solved problems in both. Now what is the mathematics behind it? Let y be y of x1 to xn, and c is delta y. Okay, so I said D is minus of C. Okay, you can put the equation numbers. You can call this as 1, this is 2. Okay, so D is actually the minus of the gradient vector. D is the minus of the gradient vector. Now, if you say what will be the modulus of the C vector? Root of dou y. Yeah, so we got this, right? Now x naught what are we trying to do? X1 yeah, can you tell me? If you tell me properly, then I'll have the satisfaction that you understood the algorithm. So x1 equal to x naught plus alpha times alpha times d naught, correct? Of course, the treatment is for a minimization problem. That dy by dx1 minus, let us treat it for a minimization problem. Otherwise, you can adjust alpha, do not worry about the sign. Okay, so this we can call it as 4. With this, okay, this is how the algorithm works. So this is the mathematical notation, I have written it in the mathematical notation, we already solved the example. Now we are curious to look at, let us look at Ci, what is the product of Ci and Ci plus 1, where C itself is given by, C is the del of y. Rather I am trying to see whether Ci into Ci plus 1 equal to 0, so that the new direction is always orthogonal to the old direction. It has to be so, but now we will prove it formally. Okay, we want to see, idea is to see Okay. How do you do that? So how did we get alpha? Minimize correct, okay. So we are trying to do dy by d alpha of I plus 1 equal to 0, dy by d alpha of I plus 1 equal to dou y by dou x at I plus 1 into dou x by dou x, one is a capital X, one is a small x. Agreed. So d is equal to into dou x by dou alpha dou x by dou alpha, okay. This x is the capital X, correct. What is dou y by dou x at I plus 1? C at what iteration? C by I plus 1, okay. What is dou x by dou alpha at I plus 1 is equal to dou by dou alpha I can't put 0, I have to put I, right. For the general notation I have to put I. So if you take derivative with respect to alpha, what do you get? Di. What is the relationship between di and ci? Minus ci. So if dy by d alpha has to be 0, dy by d alpha is itself a product of two partial derivatives, dy by dx into dx by d alpha. Dy by dx turns out to be ci plus 1, whereas dx by d alpha turns out to be ci. Therefore ci into ci plus 1 equal to 0. Therefore at the I plus 1th iteration the direction of movement is orthogonal to the previous direction, QED, okay, proved, fine. Therefore so the new direction of movement is orthogonal, perpendicular to the old direction of movement. So there is steepest descent. Which one? Last part. So I didn't do any cheating here. We actually, that's why I gave an example x1 minus 8 whole square plus x2. That's how you got alpha. You put dy by d alpha is equal to 0. I am writing dy by d alpha as a mixed derivative, not I mean as a product of two derivatives, dy by dx into dx by d alpha. Dy by dx is nothing but c at I plus 1 iteration. But if I take dx by d alpha, I can write the xi plus 1 as xi plus alpha di, because that is the way we have written it here. If I take the derivative, everything vanishes except this d. So this d is nothing but minus c. Therefore ci into ci plus 1 is, that's what we started out with. So that's why I said you go like this, okay. So this is the proof of the steepest ascent method. So last 5 minutes we will just wind up our discussion on this Cauchy's method by introducing a very interesting variant, namely the conjugate gradient method. Conjugate gradient method can be used in your project, it can be used in your research. If you say I have solved a problem with conjugate gradient method, reviewer will not say anything. If you say I have solved it using steepest descent, he will say no good, okay. and you cannot get out of a 600 level course without at least hearing about conjugate gradient. Okay, so conjugate gradient method. A very crude form of conjugate gradient method we already saw, the Liebenberg-Marquardt algorithm, when we try to do nonlinear regression, where there was a damping factor introduced, right. That gives you a rudimentary idea of this conjugate gradient. So it is better understood if you actually that is okay, huh? They have to okay, so you start with x0 and hit x1, so this is small x1 x2, right. From here you go like this, x2 what did I do x either use the subscript or superscript consistently, right. So you started with x0, went to x1, so what are we doing here, what method, the Cauchy's method, the steepest. Now some fellows thought that from x0 to x1 why go to intermediate step, from here if you do this can we go directly from x1 to x3 bypassing this. So consistently if you do this then you can jump some steps. Can you deflect the direction in which you are moving, instead of deflecting only in the orthogonal direction to the previous, can you come up with a deflected steepest descent method. So this deflected steepest descent method is called the conjugate gradient. Who will tell me what the deflection is? We will work out the mathematics, it will be just 4 lines, but somebody has already thought about it 30 years back. Okay, so this is so if you apply this funda, you go start from x0, first 2 steps are same, you start with x0, go to x1 using steepest descent, and then x1 directly you go to x3, each time you skip some steps. So this is the conjugate gradient method. It's also called the Fletcher-Powell method. Deflected steepest descent method. Is one of the most powerful algorithms ever used. One of the most powerful algorithms, it has come to stay, it has withstood the test of time. Even in circa 2010 papers are written with conjugate gradient. People, if you say conjugate gradient, people say it's okay, acceptable. Okay, so because suppose I write a paper, I have solved a heat transfer problem with genetic algorithm, simulated annealing, and I am getting this advantage, genetic algorithm is blah 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 blah, it mimics the process of nature, I write my story. Reviewers say, how does it compare with conjugate gradient method? Can you demonstrate with a simple problem that it is better than conjugate in terms of memory requirement, in terms of the speed? How does it perform with respect to conjugate gradient method? It is some sort of a benchmark. Then one Davidson also joined them. Then there is a Davidson-Fletcher-Powell method called the DFP method, that is also very powerful, right. So it is endless. So suppose somebody wants to work on the theory of optimization also, so much is there, but invariably it will be either in a mathematics department or in an industrial engineering setting. A lot of somebody who is very mathematically inclined, he wants to probe further and further, or he wants to do a hybrid of evolutionary optimization and calculus based, then you can, okay. So then what they will ask you to do is all these algorithms have to be tested on certain standard optimization problems. Okay, we will talk about this in a later class. Now first few steps, so the algorithm. Now that you do not have any quizzes and you have plenty of holidays, I would expect, I am not going to ask, I would expect at least half a dozen of you to code it in MATLAB and check with the simple problem which you have done in class, and you can show it to me. I will be glad to review it on a voluntary basis. Okay, at least some curiosity should be there, no? Some of you may not be interested. Okay, oh, why did I take this course? But I think a few of you who are really mathematically inclined, and this can be easily programmed, and I have given you example problem. You do not have to search for example problem. You have seen how the steepest descent struggled. That problem you can apply. So di, or if somebody can do it and demonstrate it in the class, we will allot some 5 or 10 minutes in one of the classes for one example problem, right? So di equal to, yeah, please see this. Di minus 1, no, it is fine. Okay, you calculate the Ci, but now I introduce a beta I. Okay, you calculate the length of del y at the current iteration and the previous iteration, take those ratios, square it, that becomes your beta. Yes, yes.
So minus Ci is nothing but Ci.
Where? Yeah, okay. There is no problem, right? Yeah, fine. Correct. Senthil, what he is saying is fine. Di into 1 minus. Okay. That is correct. Yeah, you want us, should I do that? 1 plus, you are sure? Okay. Please check whether it is 1 plus or 1 minus. What happened? No, both said di new or di plus. This is the way it is. Once you write a program, you will write like this. Okay. So now evaluate. If there are any changes required for a maximization problem, please you can rework, right? Okay. Update it. If beta equal to 0, beta equal to 0, it becomes a Cauchy's method. There are rigorous mathematical proofs as to why the conjugate gradient method is quadratically convergent. I already told you what is quadratically convergent, right? So there are rigorous proofs available, people have written papers, they have demonstrated with test examples and so on. Conjugate gradient method is really one of the powerful methods, you can see that. Okay. What? That is the algorithm. I don't have time to prove that. Hmm?
Tiwari was asking like
No, some people objected. If you leave it like this also, it's all right. You can say x equal to x plus 3, right? In the program, you can say x equal to x plus 3. Yes. Ci by Ci minus 1. We are always looking at the ith step. If it is I plus 1, you can put what you are saying. Be careful about that. See, for each iteration, to get the value of beta, you require at two other places, I and I minus 1. You require two values of C to get beta, right? Current and the previous. So you can make it beta I plus 1, Ci plus 1 and Ci, whichever way, okay. So, but two C has to be calculated at two steps. So that is why you will start with the Cauchy's method, and then only after two iterations, one or two iterations, you can switch over to the conjugate gradient. Okay, I will take attendance, we will stop here.